So today we'll focus on the total cost of ownership. The goal of the session today is to share resources that would support retailers and their partners in comparing the total cost of ownership of various natural solutions. Joined today by our wonderful presenters, Andre Patenaude, the Director of Solution Strategy Cold Chain for Emerson Commercial and Residential Solutions, and Derek Gosselin, Director of Technical Product Support with Hillphoenix. Now I'm going to turn things over to Derek to kick us off. And you are on mute, Derek, just to.
Well, we are starting off today with Andre, so I'll turn it over to Andre.
Great. Thank you very much, Derek. I appreciate it. And good morning, good afternoon, everyone. I'm thrilled to be here to be speaking with Derek this afternoon. We've talked about doing this for some time, so I'm really happy to have the opportunity to do that. The subject I'll be talking about is kind of broken into two portions. I'll talk about two studies that Emerson recently invested in. One is this total cost of ownership study. I'll give you some basics around it. And then I'm going to get a little more detail on a CO2 climate study that Emerson also invested in. I don't want to give you too much about the cost of ownership because Derek's section will get into some specific details around total cost of ownership, but to give you an idea on what is being done and the information that we wanted to get out of this. So Emerson about 2.5 years ago invested in a total cost of ownership study, as I mentioned, for these 7 architectures. Actually, we looked at about 9, but I'm listing 7 on here. Centralized DX, distributed scroll packs, medium temp and low temp, individual condensing units, CO2 transcritical booster system with adiabatic, and then with a dry gas cooler. Then we had an R290 micro distributed water cooled, was another architecture, and scroll booster using 513A. It's a low pressure system that Emerson developed. So the specifications around the store, when we set the guidelines, we said, hey, let's look at a 25,000 square foot store with 450,000 BTU medium temp, 91,000 BTU low temp. We had about 36 cases in all, 5 walk-in boxes, as you can see there. And we had a design engineering firm actually design all of these stores, these really 8 stores, we're showing 7, as I mentioned, do refrigeration schedules, electrical schedules, floor plans for refrigeration, floor plans for electrical, for all of these stores, so we could cost it out properly. Then we worked with getting pricing on equipment, work with contractors on installation, commissioning, service, maintenance over 20 years. We looked at different cities across the US so we can understand what energy they pay now and what the increases might be over a 20-year span so that we can come up with that total cost of ownership and compare one to the other. So that was the goal around it. The next slide, please, Derek. So kind of give you a snapshot. Here's that 25,000 square foot store. All your cases, medium temp cases are in green, and your low temp cases are in blue, light blue. I did not indicate the coolers, but as I mentioned, there was 5 medium temp coolers and 1 low temp freezer. So that kind of gives you the footprint that we looked at for the BTUs mentioned. The next slide, please. And the architecture we chose was, you take at the top left corner of the screen, HFC centralized. We use 448, 449 for medium temp and low temp. Moving into the middle, distributed scroll. I'm only showing one system, but we also had low temp, medium temp and low temp, and 448, 449. 2 CO2 systems, one with and one without adiabatic gas cooling. And then you go to the bottom left, scroll booster. It is a booster, but using low pressure refrigerants. We use an A2L as well. Scroll booster, not a scroll booster, scroll distributed, low temp, medium temp. And then we looked at micro distributed. Now that micro distributed also had an adiabatic cooler on the roof. And we had about 52 compressors in this particular store, for example. And the single condensing unit, we had 27 single condensing units in this size store. So some of the factors that we considered were compressors, of course, the refrigerant, as you see, the number of compressors were all listed in our details. We looked at minimum head pressures. They may change slightly from one architecture to the other to support industry standards. We looked at about low temp TDs, medium temp TDs, 10 and 15 degrees. We looked at some systems had case controls and some had mechanical expansion valves. That was factored in all those costs. We also looked at the charge. So how much charge we estimated when we designed these systems and leakage rates, because depending on the size of the system and how much piping there is, your leakage rates will vary. So we factored all that in when we calculated LCCP, energy, and costs. So next slide, please. And these are the cities we looked at. So, and what's interesting about that, when you boil it all down, and like I said, I'm not getting into specific details for each city, but it was interesting. When you look at the total CapEx on the bottom, there was a range there from about, depending on where you were and the equipment that you wanted to buy, in that 20-year total dollars, CapEx would range from somewhere between 25 and 40%. What was interesting is the maintenance piece was relatively constant across all architectures. You know, it would vary a bit, but that was probably the most constant value. And when you look at energy, depending on the city you're in, you look at Bakersfield, very high, so you're running high head pressure a lot of the year, whereas Minneapolis, you've got probably 90% of your hours of operation below 60 Fahrenheit. So that obviously has an impact on energy over time and the costs. So Derek will talk about specific total cost of ownership criteria when CO2, but this was just a snapshot to give you an idea of the level of detail that we did. And if you're interested in talking about this future, we can certainly do that. But the next slide, please. I want to spend a little bit of time on a CO2 climate study because it is specific to CO2. So this is, again, something that I was involved in from the start with a consulting engineering firm that really specialized in CO2. And we decided, well, when we look at where are we going to do this, we said, let's do the entire America. So Canada, Latin America, and the US. And I don't show all of the Americas there, the southern part, some of it is missing. But in the US alone, there was 166 cities identified. And we looked at, well, ASHRAE climate zones as well as IECC, because we wanted a bit more granularity in looking at these different zones where humidity plays a huge factor on adiabatic efficiency or not. So we'll talk a little bit about that later. We determined the cities, and then we took NREL data from TMY3 to compile all the bin data from the hours of temperature of the 8,760 hours a year. You know, how many hours did you operate in subcritical mode? How many hours did you operate in transcritical mode? And then we looked at what strategies do we really want to compare against. So we took the most common high ambient strategies, and I'll review those in a minute. And then we built an energy comparison using the EES software. And the system size that we chose was 400,000 BTU medium temp at a +18 saturated suction, and 100,000 BTU low temp at a -20. So that's very close to the total cost of ownership capacities that I showed you a little earlier. So that kind of gives you an idea of the size of the supermarket. And really our desired outcome was to provide, a basis for this study from an impartial source. So when we look at the climate zone categories, and I mentioned we used ASHRAE as well as IECC, and I carved out California because California, we talk a lot about California, but California from a climate zone perspective is special in its own right. it's got 6 of our identified 13 zones in California alone. So that's why we talk about it. And of course, we've identified cities in each one of those zones so we could have a representation. And if you need some data, we can pull that specifically for given cities. Well, you take San Francisco, for example, kind of a cool zone. It's under Marine ASHRAE zone, and it's a 3C under ICC. So that kind of gives you an idea. Next slide, please. So when we looked at the high ambient strategies, of course, we wanted to compare transcritical booster system, just a basic transcritical booster using a dry gas cooler, which is the one on the left, to an adiabatic gas cooler, the one on the right. Now, this happens to be the roof of our Copeland facility in Sydney, Ohio, where we're getting ready to start up our CO2 supermarket lab. And these are 2 of our gas coolers that, of course, we have in parallel. And we also have a 3rd gas cooler, so water-cooled gas cooler, that we could run at any time of year to achieve any gas cooler temperature to perform our testing in our lab. But so that just shows you a picture of both. Next slide, please. So what we wanted to do is say, okay, well, what else are we going to add from a high ambient strategy? Of course, dry cooler is not a high ambient strategy, but adiabatic is. So I say, okay, parallel compression is another technology that can help with energy efficiency. So let's look at that. And then let's look at adiabatic gas cooling with parallel compression or intermediate stage compression. And then we want to look at dry gas cooler if you've got issues with water availability with parallel compressor and gas ejectors, high pressure gas ejectors, and then again, adiabatic with parallel. So the next slide kind of breaks it down a bit. If you're not that familiar with the architecture, kind of built some stick diagrams. If we start on the top left corner, we're looking at a standard booster system. Now, I didn't put the oil system in there. I didn't put dump solenoid valves or filter dryers, just the line sets basically, so it's easier to follow. But you've got your dry gas cooler on the top, and then if you go down to the bottom left, I've got the little spray nozzles underneath the gas cooler. That's my indication that it's an adiabatic. So that's one strategy that's important to compare against one another because it's very popular in the US right now. It is the most popular high ambient strategy that I would estimate. However, we wanted to look at the middle of the page here, which is parallel compressor at the top and or intermediate stage compressor. You can see that of those 3 compressors at the top, one is separated from the main medium temp suction group, and you've got a yellow line going to it. And that yellow line is also connected to the flash tank. And the beauty of parallel compression is that its suction pressure is approximately, give or take, 100 PSI higher than medium temp suction because it's coming from the flash tank. That means your gas is denser and your compression ratios are much lower on the intermediate stage compressor. So you can do that. You can manage it, the excess flash gas, instead of sending it to medium temp suction, you're sending it to an intermediate stage compressor that's operating at a much higher suction pressure. So your heated compression is less because your compression ratios are lower. Your discharge temperature going into the gas cooler are slightly lower. And there's an energy advantage of doing that because oftentimes you can downsize that compressor because its capacity goes up with an increase in suction. So all that, you may find a range there of 3 to 10% energy advantage on a system by using that. Depending on where you are, it'll vary, and I'll show you some charts on that. And then we wanted to look at, well, take that same architecture with an intermediate or parallel compressor and add adiabatic. And the next step, we wanted to layer in now dry gas cooler, parallel compressor, and then you can see at above the flash tank in the top right image, there's a little image there of a gas ejector. And you can see the side port goes all the way to an accumulator at the inlet of the medium temp compressor. So your medium temp cases, vapor is going into that accumulator, your low temp discharge going into that accumulator. Now we're siphoning vapor off of that accumulator so that my medium temp compressors don't have to work as much. we want to send that to a parallel compressor. So there's an energy advantage adder to that because we're pushing more vapor to my parallel compressor for longer periods of time. So that's important to look at. And then the bottom one, we add adiabatic. So those are the main 6 buckets, if you will. So the next slide, please. So from there, we looked at all the climate zones and we've organized them. From the far left is the hottest dry bulb temperature on average for climate zone hot, dry 2B, 3B, and you go all the way down to the bottom right, you've got very cold 7 subarctic 8 zone, which is 88.8 degrees. It probably happens on July 7th of every year. But nonetheless, what's interesting about this chart is the orange. Now, the orange represents a relative humidity in those climate zones, the average relative humidity in those climate zones. And if you go to the next build, please, Derek, you'll notice that 4 of those climate zones, 4 of those climate zones are below 30%. And that's interesting because when you're drier, the impact of adiabatic gas cooling is much greater. Now above, when you build the next slide, you've got 9 out of 13 climate zones now. That parallel compression is more energy advantageous annually than adiabatic. And maybe I'll show it again on the next slide. So adiabatic alone on the far left. Now what this chart represents is all 13 climate zones listed with adiabatic gas cooler alone. And what that number, that bar represents is a decreased energy relative to a standard booster system with a dry gas cooler. So you can see that the highest ambient zone, which is a hot, dry 2B, 3B, with adiabatic alone gives me almost 14% savings. But in that same zone, you go to the middle chart, that dark blue line to the left with parallel compression by itself gives me around 8%. So the chart on the left, 4 of the bars are taller with adiabatic. Those are those 4 climate zones where you had less than 30% on average relative humidity. Adiabatic outperforms parallel compressor, but 9 out of 13, because there's already moisture in that air, parallel compression from an annual perspective outperforms adiabatic by itself. Now, if you build to the next slide, of course, if you add both of them together, you get a net benefit. It's not the sum of both, but it's close to it. And you can see significant energy savings. Again, they are all lined up from left to right, highest ambient to coldest. It kind of gives you a snapshot. When you start looking at the numbers, you start seeing some patterns develop. Next slide, please. So what I wanted to do now is take a look at this chart, spend a little time. This is hot, humid, 1A, 2A climate zones. There was 10 cities in here. But I'm showing you 3 out of the 10 cities. From the coldest, I say the coldest, on average, I say coldest because if you look at the bottom there, there's a note that says greater than 75-degree dry bulb will happen in Tallahassee 3,588 hours a year. Even though the maximum dry bulb temperature in Tallahassee is 100 degrees, it's warmer than Miami maximum dry bulb. If you go to the right now, Miami's maximum dry bulb's at 96. However, if you go to the bottom, greater than 75 degrees dry bulb happens 6,509 hours a year. So that's really important because if you don't have a adiabatic gas cooler, you can be operating in supercritical operation 6,500 hours a year. So how do you mitigate that? That's what this is all about, right? Trying to mitigate systems from operating into a supercritical operation or transcritical mode. And it varies from climate to climate, depending on humidity or not, and temperature, of course. So if we take a look at Miami, because it's the hottest hours of operation in transcritical mode. If you just had adiabatic alone in Miami, you would be saving a little over 8% over standard transcritical booster system. And you go to the gray line, if you just had a dry gas cooler with parallel compression, you'd be somewhere at about a 11% savings over a basic transcritical booster. But if you add both, you're at a 17.8 adiabatic plus parallel compression. And this is where designers and end users have to decide, okay, what's really important to my decision making, and that's what Derek's going to drill down into. Now, Miami doesn't have a problem with water. Obviously, there's water all over the place. However, you know, if you look at, if someone did not want to use adiabatic and just use parallel compression with dry ejectors, with high pressure ejectors, you're around 14% savings over a basic transcritical booster system. And of course, if you add all the technologies that I'm highlighting here, adiabatic plus parallel plus gas ejector, you'll see there's about a 1.7% advantage adding ejectors to an adiabatic plus parallel compression. So all these are factors that become very important when you go to the next slide and you start evaluating what other considerations do I need to take, you know, to look at while making my decision. Of course, electrical rate, the rate structure, peak demand charges can make a big difference on what strategies are implemented or how many strategies are implemented, because peak demand charges in certain areas can really have a huge impact on electrical bills the following year if they're not properly mitigated. Water resources, we keep hearing about shortages in water in California. So, you know, are there other strategies to get water? But if you do have it, you know, what are the charges going to be? You got to take that in consideration. Service and maintenance skill levels, of course, we've heard a talk of that in the industry. The industry is gearing up, of course, and more contractors have skill sets for CO2, but that's a consideration that retailers take into play. Heat reclaim, how much volume of heat do you need? Do you even need heat? And if you do, how much and how intense is it? And what do you need to do to the system to take advantage of it? And other things like carbon intensity, if the retailer has net zero goals, depending on what your generation sources are, your emission rates, of course, will be different, and that might have an impact on some of the strategies that you use. And I think Derek will be talking a little bit about something new that we've just heard about in the last year or two, carbon credits. So those are all obvious considerations when choosing these systems. And the next build really is about the reason we did this study and we commissioned it and used a third party in order to get that unbiased third party information around specific high ambient strategies. Now, what we did not do study on is mechanical subcooling. I didn't talk about it, but we will be talking about it in our report, kind of an extreme high ambient mitigation strategy. And we didn't talk about annualized strategies like near zero superheat or liquid ejectors, because that's kind of an annual strategy, not a high ambient specific strategy. So I think that is all I have. I'll pass it over to Derek.
Well, thanks, Andre. And as you saw, he went into a really good definition of the different types of options and the technologies that impact CO2 systems. And, you know, we'll look at that. But, you know, as Mike mentioned earlier, you need to have options. And when you figure out what option works best from you, and that can range from the micro distributed, the macro distributed that was discussed. But then we're going to focus a little bit on CO2 and that how you can apply that both as a central or distributed CO2 system. And it gives you the better understanding of what works best for you, but really look at how it impacts the total cost of ownership. So when we look at that, all right, no, it's not going. So we look at why CO2 is a refrigerant, and we understand, of course, it is a natural refrigerant. It does get us out in front of regulatory compliance because it has a low GWP. It does provide you a future cost avoidance because if you're doing a system today and it's not natural, there might be a life expectancy of that store where you may have to retrofit it. Energy efficiency. And as Andre went through, there are a lot of technologies out there that make CO2 in warmer climates more efficient. And again, where the impact comes in with carbon emissions and what you can do with the total cost of ownership with possible carbon credits. Now, if you notice, A2Ls are not listed here. And we talked about that earlier today too, where they're looking at code adoption and getting approval. So when you look at that may be a lower GWP option that you always have to consider because, you know, it's about what is best for you and having those options. So as Andre just went through, there are a lot of things we have to focus on when we talk about total cost of ownership. Part of that is, do we have the right technology so that we can address usually the first item that is always important is energy. And how do we reduce energy by having the right technology? Also, the better use of available heat reclaim. And again, we'll get into that a little bit later, but how do we use the higher pressure, the more available heat from a CO2 system? And how do we help that with the HVAC system? Looking at just not the impact of the refrigeration system, but that of the total supermarket. And again, where are you with your carbon emission goals? What your goals are as a company, and then what we can do to help you bring a value to that with refrigeration carbon credits. I'd like to talk here a little bit about what do I know and what do I need to know. And they can be a little simple, but one thing is regulatory compliance is forcing a change. So what you are currently doing today may not be a long-term option. So you have to identify what that is, how it is, and how's that impact and what you need to do. And what you do need to know is, what are my options? Can I go to a low GWP refrigerant? Should I go to a natural refrigerant? What are the impacts on not only your new stores, but your current stores? And you know, in yesterday's webinar, you saw Doug and Chris, they talked about that. Having the right strategy is easy for a new store, but how do you do current stores? How do you do a remodel and keep your store open? So you have to look at that consideration too when you look at what is the impact of the decisions I'm making. Then you know your current cost. Again, you know from the design point of view, how it impacts your construction, the equipment costs, the installation cost, your long-term maintenance cost. You know that it's a baseline. But unfortunately, we have to defer back up to the top that regulatory compliance is forcing a change. And as also discussed, whether it's an A2L, whether it's CO2, whether it's propane, your current equipment will not adapt to these new technologies. So that is going to incur costs. And that's what you have to understand when you take the time and look past first cost, is understanding that total cost of ownership of what it's going to cost you, no matter what you decide you're changing to, it's going to incur costs. And how do you understand that cost and avoid as much of it as you can? We understand, you know, the impact of energy, and it's always been a driver in our industry and how we operate our equipment, whether it's from the rack system or whether it's what our requirements are to be DOE compliant. You know, we look at that. So when you look at refrigeration, lighting, heating, and air conditioning, that's a big majority of what's used in the supermarket in general. How can we then take a look at further technology to reduce the rack side of it? As Andre went through all of the advantages of whether it's adiabatic, parallel compression, ejectors, you know, we do have some examples of mechanical and natural subcooling and how that can improve the efficiency. Also developing technology with where we're going with pressure exchangers. The industry is working, and a lot of the partners are working together to find the right strategy that can provide you that energy solution. But as I mentioned, we have to look beyond just the refrigeration system. You know, how do we do better with water and heat reclaim and improving that efficiency, integrating with HVAC, whether we can do mechanical or subcooling. And one thing that's really overlooked, but it's very important, and Andre mentioned this, a dedicated control strategy. You have to have alignment with your controls partner to make sure that the devices, the controls, and everything is set to get maximum performance, but also make sure that it's maintenance and maintained that way, because you want to also be able to keep it going forward. It's not just start it and forget it. You have to totally maintain it because they provide us advantages. When we look at technology and being able to adapt CO2 in all climates, improve your store efficiency, just not your rack. Reduce utility peaks, and that was mentioned a little bit by Andre as well. Risk management, and what am I doing today, and will I have to retrofit it if I don't do natural refrigerants? There's a risk there. And then look at sustainability and carbon reduction. That's becoming more and more of a thing within your corporate strategies. How do they all tie in together to give you the best value? And again, they will vary based on what your baseline is today and what you plan on doing going forward. One of the advantages with CO2 is you have to add case controllers and electronic expansion valves. Yes, that has an impact to increasing your case cost, but there is also an energy savings. We know that the use of EEVs can give you an 8% savings, and that helps you not only with controlling superheat, because now you have an electronic expansion valve controlling that versus a mechanical valve, but you're getting better case performance. That's something we can quantify. But it also leads to better case temperatures, better product temperatures, maybe even a food safety advantage. How do we value that? And then look at defrost strategies, having minimal effect on your product. Because at the end of the day, you are selling groceries. And how do we help you maintain that product to sell more groceries more efficiently? And then, of course, reduction of maintenance, because it's easier to do remote monitoring, to do troubleshooting without having to roll a truck to find out what's wrong in the store. So there are distinct advantages, not only that we can quantify, but things that we have to consider because they also bring value. Then you take a look at that heat reclaim. What we commonly do today in a lot of cases is we go through the three-way valve, go through a heat exchanger, put the heat into a hydronic pump skid, and then distribute that through glycol. That's good, it works, but it's not as efficient as it needs to be. How can we take advantage of that and then just go direct? Go right to the air handler, maximize the use of the heat coming out of the CO2 system on the discharge side. It allows us to be able to have direct equipment that allows that heat. It gives us the ability to go to a single unit, whether we're using it for heating or air conditioning or dehumidification. It also gives us the ability to use all of the heat. We're not losing anything and transforming it into glycol in a two-stage system. And it also allows us, by better utilizing this heat, is how do we reduce or even in some cases eliminate the use of natural gas in your heating of your store. If your system is large enough and gives off enough heat, you can heat your store by directly feeding it into your HVAC system. That reduces that use of natural gas. Not only does that provide you an energy efficiency, it also provides you a carbon reduction. And then how does that all impact your carbon emissions? By not only using CO2 and reducing your refrigerant emissions, but now you're reducing your store operation emissions by using CO2 to the best of its advantage. And we understand that because it runs at a higher temperature and a higher pressure. And how do we better utilize that? And an example of this, and it will vary, like I said earlier, everything needs to be compared to what your baseline is and what your regional area is that Andre talked about. So if you look at it and say, okay, we're going to use heat and we're going to better utilize it by direct feeding it into our HVAC system, it gives us the ability not only to reduce energy of the HVAC system, but it also provides us the reduction of natural gas. How many therms can I say? How much less natural gas do I have to burn because I'm better utilizing heat reclaim? And I think that's a big push going forward too, when we start looking at what are all the things that impact our decision-making process and how do we make the best decision? We have to look beyond just refrigeration first cost, is how does it help improve the overall operation of your store? And you heard Tristan yesterday talk about emissions. Yes, there's direct emissions, indirect emissions, and there's a third study, which is kind of a collection of all the other ones. But let's look at what the decision your refrigeration system and the impact of using natural refrigerants can have. We just showed you with heat reclaim, we can burn less heating fuel by not using natural gas and using our waste heat better. And that we also have a low GWP refrigerant that's going to allow us to reduce our carbon emissions just from leak rates. And then we look at the next step is indirect. The purchasing decision of buying a natural refrigeration system does impact your heating and cooling as well as your refrigeration. So there's an advantage there beyond just having to do something for compliance is how can we bring a value and align with your corporate strategy? Then we take a look at when we talk about that strategy is how do we get value out of that? How can we get a value of the credits that we've earned by you investing in CO2 and taking advantage of the right technology and the right application that fits your need in your region? How do we create a value? Now that value can be there if you're doing a gas retrofit, getting out of a high GWP to a low. It's not just limited to natural, but there's a bigger bang for your buck by doing natural when you reduce your whole carbon footprint of the store. So how do we then take that into a value statement? You know, yeah, you can do it in your distribution center. You can do it in your grocery store. You can do it in retrofits. So let's just take a new store or even a remodel. If you're going from a high GWP to a natural refrigerant and a remodel, what's that value of that carbon emissions credit because you're using a natural refrigerant? We have to be able to do our homework to understand where the values are so that we make the right decisions. One thing that we do know is the parity between HFCs and CO2 systems are closing. It used to be a lot when we first started this back in 2009. It is very much reduced now. Now our costs are going up and that's more supply chain, but it's going up across the board for all of our equipment. But the comparison between the two designs is coming down. So how do we take advantage and understand if our costs are coming, excuse me, if our costs are coming down as far as comparative to our baseline, we understand that refrigeration installation is going to be lower because we're going to use less refrigerant at a lower price point. We're going to be able to save on the install by having smaller line sizes, which leads to lower labor installation and so forth. That can be valued, that can be calculated. So when we look at the comparison now, the cost difference is we just don't look at the capital cost. We need to take into effect what are the savings when we look at installed costs, because we understand that it does provide us a lower total installed cost. So when we start doing evaluations, comparisons, or even putting it into an ROI statement, we have to understand any and all opportunities of what that price point is. So if we take a moment and look at that ROI, we know the cases are going to cost more because we're adding case controllers, EEVs, and a few extra sensors. We understand the refrigeration systems are going to go up, but we also understand that your refrigerant charge will be a little less and per pound will cost a little less. How do we evaluate that savings? And then, as I mentioned, there's a savings in installation. And all you have to do is partner with your install company, and we can work with you and your OEM partner to find out what that value is. So that when you look at your total installed cost, that's a little bit less than just the first capital cost. And it's important to know where your starting point is, because there are a lot of options. Some may apply, some may not. How do we use the right equipment and the right technology to get the best efficiency for your store in the regional climate you operate in? How do you gain out in front of regulatory compliance or cost avoidance of future retrofits? And they really get into effect. If you're in California, you're worried about your weighted GWP. So where does using CO2 help you in being compliant? And then if you're going forward with current refrigerants, what is the impact of cost avoidance? If you do CO2 today, you do pay a little bit more, but you will not have to retrofit that store. How do you do refrigeration carbon credits? Again, another advantage of using CO2 is your reduced carbon emissions. Create a value for that, whether you keep it for your corporate strategy or you sell it on the open market, there's a value there. How do you create that value? Understanding what we talked about with heat reclaim. If you can use your heat reclaim more efficiently, reduce your energy efficiency of your HVAC system and reduce or eliminate your natural gas, that can be calculated. That is a net savings. So when you put that together with incentives, and you know Danielle and the whole team at the NASRC is working with CARB. They're working with all of the state levels, working with utility companies. What is available in your area that can offset your first cost to provide you that long-term solution? So when you really look at it is, when we talk about total cost of ownership, it's really about doing your homework and understanding what are the things and what is the information available to you so that you can make the right business decision. Again, this is targeted here today on CO2, but it doesn't matter what you're going to. You have to transition from what you're doing to a newer technology. And in order to do that, you need to inform yourself so that you can make the best technology. And again, as it's been stated, there are a lot of options out there. CO2 might be the best, but it's not the only one. You have to figure out from a cost point, how's that impact your operations and how it helps you with providing the long-term solution. So with that, I'm going to go ahead and switch it back to Danielle and see what we have for questions, and bring back in Andre and try to do what we can.
Great. Thank you so much, Derek. Thank you, Andre. And just a reminder that if you have a question, to please post it in the Q&A section. We did have a question come up, and Andre, I think this one's for you. And when you were introducing the different components, cost components included in the study, you talked about the cost of service, and, you know, did that include an all-encompassing, you know, cost of service and maintenance, or was it just the labor?
No, it was an all-inclusive contract. So we looked at two contractors, one in the East Coast, one in the West Coast, and it was amazing how close their numbers were. Cities may have had regional, very, you know, slight variations, but that included everything.
Okay. And was there a percentage decrease for the use of adiabatic condensers by city? Sorry. For the savings, the percentage savings associated with the adiabatic condenser, was that for the whole year, or what were the peak savings?
It was looked at both. So we looked at annualized as well as peak, because even though one strategy may not look that great annualized, when you add peak with adiabatic, you go, whoa, in that specific city, it made a huge difference. So, and that's to Derek's point. Those are things you have to consider out of those, you know, those 6 bullets that can reduce your total cost of ownership. You do have to look at each one of them individually and see how it impacts your total cost.
Great. And, you know, a question for both of you, and you've both been part of these conversations where together with our retailer members and engineering partners, we've been exploring, you know, what it would look like to produce a tool, total cost of ownership tool that anybody could use, you know, that was open source, transparent, you could see the inputs and outputs, and for a retailer to input their specific information and it spit out, you know, here are the different total cost of ownership based on these different options. You know, what do you see as some of the challenges associating with developing a tool like that? And what would you advise to retailers who, you know, really want to use their own data and see their own data in such an analysis?
Yeah, it's a great question, and I can start. Maybe Derek, you can finish, but we're going through that exercise right now, and it's been ongoing for over a year now, because now that we're pulling the total cost of ownership study we did, there's data there, and we've got climate study data. So bringing those two together into a tool is really a challenge. To Derek's point, prices are changing, and if you know, we all know that prices have gone up like crazy. So keeping a tool up to date is very difficult, and making sure you've got industry partners to keep double checking these prices. That's the real challenge from an equipment and parts perspective. You can estimate energy, you can do that sort of thing, but when you're starting to look at a real total cost of ownership study, tool that you're talking about, and Derek, you can appreciate that better than anybody. There's thousands of parts that go into a system, and there's a lot of variables. So even though we're trying to have a go at it, keeping a tool like that updated to have relevance is going to be the biggest challenge.
Yeah, and I agree, Andre. And I think there are companies, third-party, neutral people, even your engineer of records can support you. There are other companies out there that can help you be more transparent to the numbers and so forth. But at the same time, I think it's just aligning with the right OEM partner And to Andre's point, things are always changing. Can we develop maybe a checklist and a simple guide to rough math? Yes. But as you know, we have a hard time validating energy based on using the right tool that third parties will agree upon with utility companies and so forth. So if we can't even manage that as an industry, how could we manage this? Because it is a big picture. You know, I guess when you look at total cost of ownership, the one takeaway I would want you guys to have is first cost is what you are spending in that transaction. An ROI, no matter how you do it, or a look at total cost of ownership is what you are saving because of that transaction. That could either be a one-time by incentives or annually by reduced gas, reduced energy, and so forth. It is so variable that I would say it would be hard to do it. And that's why I always say every ROI, every comparison will all vary based on what the individual end user's moment in time is, what he's doing today, not yesterday, not tomorrow, what he's doing today, and then what are the impacts with that. And that is so variable that I would love to see a tool. I would certainly share our ability of what we do to divest and dive into the information. And the information is all there. I would always open up my books, if you want to call it that, to say, this is how I got to this information, this is why, and so forth. But I don't think there's a tool out there, but would love to help develop one if that was possible.
Great.
Yeah, as we go down this road, we we'll find out things that maybe we need to standardize on XYZ, and this is what we use, and this is why we use it, and then there's variables from that. So we'll have to simplify it more than I think what we're trying to do right now.
Yeah, no, it's a great point. I mean, that was one of the challenges that came up on the retailer side, was even just getting agreement on what would the different baselines look like, what would the different outputs look like. And right now there's just so much variation. You know, it's the opposite, I guess, of standardized in terms of system architecture.
Right.
Great. Another question. So do you anticipate that the HFC phase down here in the US will make CO2 and I'm assuming other options more attractive because of the increasing cost of HFCs? And we were talking a little bit before this and chatting about Chilventa European conference, where what we saw was on display a majority CO2 and other natural refrigerants. And I think from my perspective, that was absolutely driven by cost of HFCs. Do you anticipate something similar like that happening here in the US?
I would think that the cost of HFCs will be going up, and especially if you start to see more rulings. I know New Jersey just put some record keeping in place. California just amended that you now can't use virgin. It's got to be reclaimed. So they're going to start to really squeeze out where and what the access is to HFCs. And we talk about choices, and whether it's propane, it has some restrictions. You talk about A2Ls, that's going to be down the road. I think from a point of view only from looking at CO2, it's available now, it's here today, and it can start providing you that solution. Doesn't mean you can't adjust from that as things get developed down the road. But I think going forward with an HFC strategy is deferring the costs, not eliminating the costs.
Yeah, I would agree, Derek. I mean, one of your bullets was cost avoidance, right? Yep. And I remember one of our end users in Canada was early on the CO2 journey, because they didn't want to have to retrofit their stores in 4 or 5 years, so they went CO2 right away, and they've keep doing CO2. They were early adopters, so they learned a lot along the way, but that was because they didn't want to have those mid-tier refrigerants go straight to the end solution. So yeah, I think that will continue to happen here.
And that's another point too, when we look at transitioning, whether you get out of HFC, HFOs into whatever the technology is, being CO2, propane, or even the A2Ls, is it's going to require a case change. It's going to require equipment change. It's going to require some different standards in your installation. So the impact of that change, and that's what I mentioned earlier, is what do I need to know? You need to know that whatever the changes are you're going to make are going to cost money. You just got to affiliate what that cost means to you.
Sure.
Yep.
And when you're looking at, when you're looking at the best total cost of ownership system for any particular retailer, what do you think it is that state or other policymakers can be doing to support that choice? Despite maybe upfront costs or other barriers, what can be done to make sure that retailers can more easily choose the lowest total cost of ownership system?
I think they have to do their homework, it's really the math behind it. Even Mike today, when he was mentioning, micro distributed and not having any of their stores focus on one particular solution is going to probably be the answer for most people. Whether you have small format, large formats, centralized distributed, whether you have, whatever your footprint is. And then you get into, am I in a urban multi-level story thing? That might be one solution versus I'm a ground up stick build in a plaza. That may be another build. So I think when you look at it, the HFOs that we've been doing provided some flexibility. It didn't matter what the application is, and it had limited impact. I think as we look at whatever the design is going forward, centralized, distributed, macro, micro, whatever it is going to be one answer may not fit all. So I don't know. It's going to be dependent on what that individual retailer has for current fleet of stores, what their building types are, and what is the right solution for them.
Yeah,
And to offset the first cost, right?
Right.
Yeah, and to your point, Derek, had conversation with retailers as well. It doesn't mean there'll just be one solution in one store anymore. They currently have multiple refrigerants in their stores, so it's very convenient. We have retailers already. It's CO2 and propane and combination thereof, right? So it's not just one or the other. I think that we'll continue to see a mix based on the application. And to your point, what type of store? Is it a remodel? Is it a new store? And that changes, of course, the equipment choices and the reasons why.
There's a question here about the cost savings associated with the CO2 rack system. And the question is, does the reduced pipe diameter alone offset the increased cost for the high pressure piping required for CO2 installation?
Well, no. If you're looking at an HFC to a CO2 store, your store piping, everything from the rack into your store will be less because it's lower, smaller size, less insulation, less pipe hanging support, as well as lower labor. It doesn't offset. It probably depends on what your contractor. That's the majority of your piping in the store. There is an upgrade for having to do high pressure copper from the rack to the gas cooler. But in a lot of cases, that's a shorter run and larger diameter, but shorter run. So that's again why you have to look at your total cost. Are you looking at a distributed system where your charge will be actually less because you're shortening your pipe runs? And that was discussed earlier. There's a lot of things you can look at reducing costs. It's about understanding what's the best fit for you, but you got to look at the whole thing.
Another question, why can't we capture CO2 from the pressure release valve to reuse in a tank large enough for expansion during a power outage?
That is a great question. There are ways you can put a condensing unit on it to keep it refrigerated on a backup generator or maybe a small battery pack. There are things like that. But one of the challenges we have is even on service and maintenance, there are no tools available today to reclaim CO2. So it is commonly vented because it's easier, and then you just recharge it, which can impact your leak rates. But from that point of view, it is something that's a challenge. It's something that you need to discuss with your service provider of what are the advantages of investing in alternative designs or equipment that allow you to keep the charge in the flash tank without venting, refrigerating it, or whatever precautions are needed. But that is a challenge.
Yep. Agreed.
Great. Question for you, Andre, in the study. the question is, what is a pressure exchanger and why wasn't it included in your study? I guess I might reframe that just to say, there's probably a number of different technology iterations, looking at a pressure exchanger on your roadmap?
Yeah, pressure exchanger is a new technology, and we decided to use, technology that exists and commercialized right now. That's the reason that it's commercialized technology around the world being used today.
Another question going back to what you were saying, Derek, about CO2 systems and the inability to reclaim. Can you build a CO2 system that won't release the charge during a power loss?
Well, the answer there would be yes. You can put a heat exchanger in a small condensing unit so that all the CO2 migrates back to the flash tank, and you keep that cooled so that it stays below its critical point, therefore not keeping it as a liquid versus a vapor, because it'll only vent with a vapor when it has too much pressure in the tank. So yes, there are ways to doing it, and there are things that you can do with either add-ons or have included in your systems going forward. Just let them know that it's a concern to you because you have brownouts or power outages, or you're in a hurricane area or storm area. Those are things that need to be considered when you, again, look at your regional advantages or disadvantages, that you can plan for that accordingly.
Yeah, and as the system gets smaller and smaller, I think that those questions will be asked more and more, right? Because the charges are small, and a condensing unit, for example, that we're starting to see them more show up. It needs to be either designed for a very high resiliency or have an expansion vessel, but that's an extra cost, an extra space that the gas can expand in a large volume area without having to add auxiliary units or building a system to high resiliency. But those are, things available. And I think we're going to have more of those conversations as condensing units make their way out into the field more and more.
Okay. And then finally, Andre, if folks want to learn more about the total cost of ownership study, where can more information be found? Is there going to be a report coming out?
Yeah, you can contact me directly at my first name, andre.patenaude@emerson.com, and I can make sure that they get the information they need.
Yeah, if you visit the Emerson booth on the platform, and I think the contact actually goes directly to you, Andre. So
okay, great.
Wonderful. Well, want to thank you both very much for your excellent presentations and sharing this information today. And for everyone else on the line, we'll see you at the next session.